Okay, so very quickly, let me just review where we ended last time. So I argued to you that if you ignore valley coupling in the original band structure, which is present but small, then you can assign a topology, particular topology, to the two bands which used to touch in the absence of the aligned boron nitride. You can think of them as sort of a superposition of a Chern plus and a Chern minus band. You can kind of see that if you think about the winding number of the two Dirac points in the Brillouin zone, namely that it is the same. And then you can convince yourself rather quickly that adding a trivial mass, so unlike in graphene, if you were to just add a boron nitride mass, you would not end up with a quantum anomalous Hall state, because in a graphene, the winding numbers are opposite. Here, the winding numbers are the same, so the boron nitride would split it into Chern plus and a Chern minus band in energy in a particular valley. The opposite valley will then have a flipped Chern numbers. So in particular, if you have a filling where you would require one of these bands to be, let's say, occupied by holes, and the system prefers to do that for one reason or another, I didn't explain that part, then you would end up with a quantum anomalous Hall state, and I showed you there's experimental data that supports that on samples which are aligned with boron nitride at nu equal to 3. Interestingly enough, the same group would claim that if the sample is not aligned with boron nitride, then at nu equal to 3, the system is a Chern 0 insulator. Okay, so it depends whether there's an alignment or not. All right, so that sort of finishes this part of the first lecture. And now in the second part of the lecture, what I would like to do is construct the Wannier states for this Hilbert space spanned by the 4 narrow bands. So now we're going to include both valleys. Then project the 1/r Coulomb interaction and try to solve the strong coupling problem. All right, so we go back to, yes, please.
Why does the exchange interaction favor valley instead of spin?
So I'm really trying to get to that point in part 3. I wouldn't want to discuss it right now. But I will answer your question. If I don't, please ask it again. All right, so we go back to our tie binding problem, which has all the valleys included. And as I said, the local density of states is peaked on this Moret triangle lattice. This was already shown in the original paper. The peaks are on the AA sites. Now, it turns out, however, that the centers of our Wannier states, which will be exponentially localized in all directions, despite the presence of the topology, cannot be chosen to be centered on the AA site. Rather, they need to be chosen on the dual lattice. So the L1 and L2 will span the triangular Moret lattice, and these are the sites of the dual lattice. So you can sort of expect what's going to happen. If the center of the Wannier state is over here, let's say W1 is centered over here, in order for us to reproduce this kind of a local density of states, that object needs to have peaks here, here, and here, not where it's centered. Right? Otherwise, we would end up with a honeycomb lattice of the peaks in the density of states. And this is indeed what's going to happen. So our Wannier states will end up looking like this 3-peaked object, which is hopping around. So again, this would be the AA site, AB, and then BA. And turns out once we construct one of these Wannier states, we can construct the other 3 by symmetry. How does this work? There's a well-described procedure for this by Marzari and Vanderbilt and collaborators in this review of modern physics. So the basic idea is the following. Remember, our 4 bands, not including spin, they're composite. In other words, they have degeneracies. And so you shouldn't expect to be able to create exponentially localized Wannier states for a particular energy band. Rather, you should be thinking about this composite set of bands and creating Wannier states for the entire composite. That's because that composite is separated from the rest of the states by a gap. So what this tilde represents here is that this is a block state labeled by a discrete index. J will run from 1 through 4, but it's not necessarily an eigenstate of the Hamiltonian. Okay? So it is some linear combination of the actual Bloch eigenstates. Now, that linear combination is described by some matrix, which we would like to be unitary, and we would like it to be such that this object is as smooth as possible in the momentum space. Why? Because if it's smooth in momentum space, then when you perform the Fourier transform, it will be well localized in real space. Okay? And you can kind of see that this will be impossible if you have Dirac-Tatric points, right? You don't want to separate them into high energy and lower energy, because at the Dirac point, you will have non-analyticities, and they will preclude nice localization of these states. So how do we find the unitary transformation that will take us from the energy Bloch eigenstates into these smoothed out Bloch states? One useful procedure, again described here, is to pick a trial state. So this G1 is some function that is peaked or centered, better yet, at the site of interest. So in our case, it would be centered over here, and it will have some structure. It doesn't actually matter too much what that structure is, as long as it is localized. Then we project this onto the subspace spanned by our Bloch states. That will give us some, at every k, some 4x4 matrix A that mixes our 4 Bloch states. Now, unfortunately, this matrix itself is not unitary, because this was chosen sort of ad hoc. But you can, if you wish, try to do Gram-Schmidt orthogonalization of these, or better yet, do SVD decomposition of this. And as long as the diagonal part of the SVD is non-zero at every element, you can just replace that by ones. And then you will turn this into a unitary matrix. Okay? And as long as this doesn't have any zero SVD eigenvalues, there's no obstruction to doing this. Okay? And so this is an example of doing this particular calculation for a particular choice of this G1. So what is plotted here is the ratio of the maximum to minimum SVD eigenvalues. Remember, if one of these SVD eigenvalues was 0, this ratio would go to infinity, and that would signal an obstruction to building exponentially localized Wannier states. But as you can see, it's always finite. Okay? So there is no obstruction to building exponentially localized Wannier states for the 4 bands. That's not entirely unexpected, despite the fact that they have a non-trivial topology, because the set of 4 bands does not carry Chern number. And the only true obstruction to being able to build exponentially localized Wannier states is having a finite Chern number. Once the Chern number is 0, even if there is a non-trivial topology, strictly speaking, there isn't an obstruction to exponentially localized Wannier states. And not surprisingly, this is what they look like. They are centered in the centers of these triangles. That's the dual lattice, the honeycomb lattice, but they are peaked on the triangular Moire lattice, AA sides. So we are not dealing with a simple Hubbard model of a bunch of nice little exponential peaks which are hopping on a triangular lattice with some Hubbard interaction, but rather we're dealing with these sort of 3-peaked objects hopping on the honeycomb lattice. And it's these objects that are Coulomb interacting with themselves. So this is a...
Are those eigenstates?
Of what?
Of your Hamiltonian?
Of course not. Wannier states are not eigenstates of the Hamiltonian.
So what do we mean by construction of linear for isolated bands?
So remember, we have 4 bands. Right? They're isolated from the rest of the spectrum by gaps. Right? Now, this is usually described by a set of Bloch states, which are delocalized. But we would like to form a local basis which spans that Hilbert space, onto which then we project the Coulomb interaction and try to solve the strong coupling problem. Does this make sense?
I see, yeah.
Okay, yeah.
Just curious, in practice, when you're doing this, it just, you go to some program, it automatically optimizes the localization.
Right. So at this point, I only described the first step.
Right.
The first step of it is so-called the projection method. And so if you find a good ansatz here, then they will already be almost as well localized as if you then try to optimize their localization. But then you can follow this initial step by the algorithm developed by Marzari and Vanderbilt, in which then you optimize the spread of these functions. And what you find out is that when you do that, you gain about 20% on the spread. So what you do lose is you lose almost, as I will discuss, you will lose almost perfect valley polarization once you do. You don't have to, because you can just compute the ratio of the SVD eigenvalues. As long as that's finite, your eigenstates are exponential. Okay, but yeah, you can check that they're exponential, and they are.
But when you're optimizing it, are you?
No. When you optimize, you compute the spread. So what Vanderbilt and Marzari compute is R squared, basically. The expectation value of position squared operator, or R minus the center squared. All right, so that's W1. It looks like this. It's split into the top layer sublattice A, top layer sublattice B, bottom layer sublattice A, and bottom layer sublattice B. Now, once you give me this W1, it turns out that these are complex functions, and they have under threefold rotation, they will pick up a phase 2 pi over 3. So they act a little bit like P plus IP type states that Liang was describing before in his work. And the other one you can construct simply by complex conjugation. Okay? So once you have this one, the time reversal symmetry will take you between here and here, and of course vice versa. Okay? So once you have W1, you can create W2 simply by time reversal. So time reversal is now implemented on site. And then to get the other two of the 4 Wannier states, to describe our 4 bands, you simply perform this twofold rotation I described earlier. This is the twofold rotation going through the plane of the board. Acting on W1, they will give us W3, and then acting on W1 with complex conjugation, so time reversal will give us W4. Okay, and then of course, you can translate this to the other unit cells. And if you go back to the original Hamiltonian, project the kinetic energy part of the Hamiltonian onto this basis, you write your tie binding model and you solve the tie binding model, this is the set of spectra that you get. Okay, so you can reproduce it. Now, there's a discussion in this field about obstruction, and I think it is important to go back to this. As I mentioned, the only true obstruction to building exponentially localized Wannier states is if the set of isolated bands has a non-zero Chern number. In our case, that's not the case. The claim is, however, that if the C2T symmetry is exact, and so is the valley U1 symmetry, then there is an obstruction to building exponentially localized, and now here comes an important adjective, symmetric Wannier functions. So in other words, in addition to asking for exponentially localized Wannier states, you would also like your Wannier states to transform in a simple way under these symmetries. And it turns out that if you insist on this, then the Wannier functions cannot be made exponentially localized. So the topology does appear, but only at kind of a higher level. It's not like in a quantum Hall where there's nothing you can do. As long as you have an isolated lambda level with a finite Chern number, you cannot build exponentially localized set of Wannier states, which is complete. In this case, you can do that, but at a price. And the price is that some of the symmetries are not represented in a simple way. Okay? The Hilbert space is still complete. Your transformations are all unitary, so you're not losing any information, but you're paying some price for the full exponential localization.
But you can break one of the 2 symmetries?
That's exactly what I'm saying. So, and in particular, in the lattice calculation, this is not a symmetry. And actually, strictly speaking, neither is this. So in that sense, if one is purist about it, in the tie binding lattice calculation, there's no obstruction period. All right, so I think I discussed this. Yeah, so this is this point. In our case, the C2 double prime is not a symmetry. And because the C2T is a product of C2 double prime and C prime and time reversal, that symmetry is strictly speaking not present, even though it is sort of emergent. So neither U1 valley nor C2T are strictly exact, and therefore there is no obstruction, even in this higher order sense. So in practice, if you do what I just showed you, without going through this algorithm of making the Wannier states even more localized, and thereby gaining about 20% on the spread, you get about 9-to-1 valley polarization. Although if you do it the way Liang and Koshino did it, you can get 100% valley polarization because you're starting from the continuum model. And then if you minimize the spread, you will lose some of the valley polarization. All right. Now this is actually connected to some earlier work on the 2D TIs in the non-trivial phase, where it was shown by Solyanov and Vanderbilt that it is indeed possible to build exponential localized Wannier functions in the Z2 non-trivial phase of 2D TI. And that's because, of course, the two isolated bands in that case do not carry a finite Chern number, but again at the price, namely that they are not Kramer's partners of each other. So time inverse symmetry is not represented locally. All right, so this is going to be our basis. We're going to have these three peak objects hopping around, and we'd like to project the 1/r Coulomb interaction onto this.
Sorry, still want to go back to
This part?
part 2 a little bit. Yeah. So under C2T, you showed these so-called fidget spinner Wannier functions. So that does not locally respect that symmetry, right?
Correct.
But if I just enforce the C2T operation on one of the fidget spinner, what would it become?
No, so you can't do that. So if you try to enforce C2T, you'll have to enforce it at this level of your trial function. Okay. If you do that, you will discover that this.
Enforce C2T. I'm just doing C2T on what you get for a Wannier function.
Then you get a linear superposition of Wannier functions outside of that site.
That at first sight looks the same, but if you look at the wave function, it's different.
Correct. Exactly. Exactly. So the bumps will still be at the three peaks, but the actual structure inside is such that if you project it onto your basis, you will get a superposition from outside. And that has to interfere to build this back up. But let me actually make a point, because it's related to what you're asking. If you try to enforce it at this level, what you would discover is that this matrix will have 0 SVD eigenvalues. And you see the obstruction explicitly. Okay.
So zeros happen at points or lines?
Points.
Is that a general statement?
SVD zeros?
Zeros as enforced by topology.
Of the SVD eigenvalues? I don't know. We didn't try to make it obstructed. Okay, so now let's go to what I think is the interesting part, namely, let's try to project the 1/r Coulomb interactions onto this Hilbert space. So let's go back to the physical problem. It's sketched over here. We know experimentally that we have these 4 bands. They are separated from the remote bands, and these are relatively flat. They're separated from the remote bands by a gap. That gap from transport activation seems to be about 30 to 40 MeV. It may be a little bit higher than that because transport typically underestimates this. The bandwidth, as I mentioned, theoretically comes out about 10 MeV, maybe less. Experimentally, based on STM, when you tunnel into these, when they're either fully empty or fully occupied, it's closer to about 20 MeV, maybe a little bit less. And then if you look at the electron-electron Coulomb interactions between 2 charges that are separated by a Moret lattice spacing, so about 13 nanometers, with the dielectric constant of the boron nitride in which it is encapsulated, the Coulomb interaction will come out to be about 25 MeV. So you see, these energy scales, they're all comparable. Okay? And so we are clearly in the intermediate coupling limit, and this is the hardest place to be in theoretical physics. Now, but in my opinion, there is a hint from the experiment, namely that the insulation, when it occurs at commensurate filling. It occurs when you are either 1, 2, 3, etc. Carriers per unit cell. You can see that here and in Dmitry Efetov's data as well. So that, I think, is difficult to reconcile with the notion that the insulation is due to Fermi surface nesting, or the Van Hoff singularities, because such band structure features would generically occur at incommensurate fillings. And then we also saw that we need to fine-tune the twist angle, or if we are off the magic angle, we need to fine-tune the pressure to get into the interesting regime where we see the correlated phases. And this suggests that the effective Coulomb interaction, even if it is not much larger than the effective kinetic energy, it still dominates the effective kinetic energy. And so even if the physical system is ultimately in an intermediate coupling regime, perhaps a strong coupling approach may be more successful in capturing the nature of the correlated phases. And so in this approach, you would take the interaction only Hamiltonian, project it onto the narrow bands, minimize that first, and then treat the kinetic energy as a perturbation. And that's what I'm going to try to do. Now, let me start with setting up some false expectations. So I'm sure most of you are familiar with the simple problem of, let's say, atomic limit insulator, where we would have one site per unit cell, so let's say square lattice, and this can be occupied with either spin up or spin down electron. Now imagine that we are in a strong coupling limit, so that we are trying to solve, let's say, the Hubbard U problem. The first thing we would do is we would ignore the kinetic energy. If we are at one particle per unit cell, then the best thing to do is to occupy each site with just one particle, because double occupancy would cost us U. But of course, we are free to assign spin up or down on each site. This term doesn't tell us whether it should be up on this side and down on this side, or vice versa. So we have 2 to the n-fold degeneracy of this ground state. Then what we do to lift this massive degeneracy is we bring the kinetic energy, which is a hopping term, as a perturbation. And the simplest process would be to hop from this side here and back virtually. And as you can see, when these spins are anti-aligned, that process is allowed. When the spins are aligned, that process is blocked. And since in the second order perturbation theory, you always lower the energy, if it's possible, to have the matrix element, you will want to go into an anti-aligned configuration for spins. This is something that you've learned in textbooks. So when you expand around this strong coupling solution in small kinetic energy compared to the Hubbard U, you find that the ground state is an antiferromagnetic insulator. Okay? Now what I want to point out is that this is not what happens in the strong coupling limit in the magic angle twisted bilayer graphene. In particular, because the nature of our localized states is not like this. Remember, it has this peculiar 3-peak structure, and so the overlaps of the Coulomb integral are a lot more complicated and interesting. All right, so here's the actual schematic of the experimental setup. The twisted bilayer graphene is here. It is encapsulated by boron nitride, and then there are gates, metallic gates. Now, the length scales here are interesting because, as I mentioned, the period of the superlattice is about 13 nanometers. And the distance to the gate can be measured in tens of nanometers, but it can be made smaller than 13 nanometers. Why is that interesting? Is because if you have 2 metallic gates and you place a charge in the twisted bilayer graphene, so in here, then you will produce image charges because of the presence of the metallic gates, and because you have 2 of them, you will produce an infinite set of these image charges. And so the Coulomb interaction at distances within a plane away from our test charge will therefore not be 1 over r at large distances. It will be screened by these image charges. And if you solve this simple sum in the asymptotics, you discover that it is exponential with the distance set by the separation to the gates. Okay? So imagine for just a second that this separation to the gates is comparable, but maybe a little smaller than the Morley lattice spacing. Okay? And then let's write our Coulomb interaction in the Wannier basis. So this is a density operator. This is a density operator. The r and r prime, they live in the entire space. And this would be the screened Coulomb interaction, screened by the gates. Okay? Now, let us set it up in such a way that we describe this little r in terms of a triangle lattice vector, capital R, which will always point to the center of a hexagon, and then a little script r, which lives inside of this hexagon. So if you were on a lattice, there's something like 11,000 carbon sites within this big hexagon. Okay? And so then we rewrite this sum as a discrete sum over the centers of the hexagon, and then an integral, if you wish, or a sum over the script r within each hexagon. And then you go to the next one, and then you sum over here, you go to the next one, you sum over here, etc. Now, if our Coulomb interaction is shorter ranged than the Morel lattice spacing, then in this double sum, to a good approximation, I can drop all the terms where capital R and capital R prime are different. So let's do that. Then it will only depend on this script R. And simply by brute force evaluation of these Coulomb integrals, we notice that the result, to a good approximation, looks like this. We can pull out a constant, which is of the order of the 25 MeV that I mentioned. And then there's a sum over the triangle lattice, so center of the hexagons, that's the sum over capital R, and then an integral of a density operator within this hexagon. And then what we do is we rewrite this density operator in terms of our Wannier functions. So to give you a sense about what sort of terms you will pick up, imagine you are doing this integral over the central hexagon, this one over here. And let's say that our Wannier state is centered on this red dot here. Then as I showed you, it has this three-peak structure. It will overlap, obviously, with another Wannier state, which is centered on the same side. If you perform the integral through a central hexagon, clearly that integral will be non-zero. So this object will contain a term which is something like a d dagger I di, where I labels this sum. Okay? But you see, you can hold the first one fixed, and the second one can move to this side. And as long as the integral is performed only through a central hexagon, there's no reason why that Coulomb integral has to vanish. And so you will also pick up a term in here, which is d dagger I and dj, where j is one lattice spacing away. That does not show up in the Hubbard model. Hubbard model only had a density type terms. Okay? Now not only that, but you see that they overlap, even if they are on this, on these two sides, they still overlap through the central hexagon. This one, and this one. So this three-peak structure of the Wannier states leads to interactions which are beyond the Hubbard model. Now, but there's an interesting constraint that we have. So we know that the Wannier states have to be orthogonal if we compute the overlap integral over the entire space. Now, if we look at this particular configuration, clearly the overlap is appreciable only through the integral over this hexagon and this hexagon. The rest is going to be small. Because they have to be orthogonal to each other, these two integrals have to cancel. Now at this point we cannot say whether this is large and this has an opposite sign and is still large, or whether they are both zero. There would have to be some symmetry which relates the two. It turns out that that symmetry would have been the symmetry that is impossible to implement locally. That's the C2 double prime symmetry. In other words, it would be a twofold rotation about this axis. If that symmetry was respected by these Wannier states, then you could show that this integral would have to be equal to this integral, and because the sum is equal to 0, each would have to be 0. But that is exactly the symmetry that is obstructed by the topology. And so when you compute this integral, you discover that this is of order 1, and this is of order -1, let's say. Now, on the other hand, if you look at this overlap integral, then the peak is only through the central hexagon, and little anywhere else. And since they have to be orthogonal, this overlap integral is going to be small. So when you open up the bracket here, you discover that you will find terms which look like density. So that's this term, d dagger I di, on each one of these 6 sides. And then inside of this square, there will be terms which look like a hop. Okay? So d dagger I di plus 1, but not I plus 2. And because this edge is related to this edge, because it's this, by translational symmetry, it's the same hexagon, you can show that the signs will be staggered between this edge and that edge. So it's will be plus, minus, plus, minus, plus, minus, let's say. So our interaction to a good approximation has this form. It's a square of an operator, and this operator itself contains a term which looks like a sum of charges on the vertices of this hexagon. That's this n of r. And then in addition to that, there's this hop-like term, the t of r, which takes the electron from here, hops it over here. And it does that with the staggered sign. And as I said, this coefficient alpha 1 is of order 1, something like 0.7. And then once you perform these sums, then you square it. Okay? Now, at this level of approximation, the leading terms, remarkably, have actually an SU4 symmetry. In other words, you can freely rotate between the spin and valley. This is not an exact symmetry, but the largest term in the problem indeed has that symmetry. If this coefficient, alpha 1, were 0, then all you would have is a density-density type terms, and this would be almost like a Hubbard model. It would be it's called a cluster Hubbard type interaction. And in that case, you indeed would not know which way to assign the spin or the valley on each site. And you would have a massive degeneracy of your strong coupling manifold. But as you can expect, once alpha 1 is non-zero, there are additional terms, and these additional terms will induce correlations among various sites without ever bringing back the kinetic energy term. It all happens at the level of a projected interaction. Now, these two operators, which contain these density terms and indeed these bond hopping terms, when you look at them on different nearest neighbor sides of the triangle lattice, they share an edge. And because they share an edge, they do not commute with each other. And therefore, the interaction, just simply projected Coulomb interaction, will induce correlations among various sites. Okay? So now let's try to see whether we can say something about what sort of states this would favor. All right, so imagine you take this form of the interaction Hamiltonian, and then you add and subtract a 0 inside the square. So this n is a constant. We will adjust this constant as we go along. And then you open up the bracket. The first term that you get is this OR minus n quantity squared. Then you get a cross term, and then you get and then you get the constant squared. Now, because this O contains a density term and then the staggered hopping terms, whose sign changes, when you sum over all R, this object will simply turn into a density. It turns into a total particle number. And therefore, if you fix the particle number sector of interest, this is a constant, and so is this. So now you have a Hamiltonian, which is a set of positive definite operators. If you can find a state which is annihilated by each one of these constants, by each one of these positive semi-definite operators, you have found the ground state. Okay? But it turns out that for n equal to 2 or minus 2, so 2 particles or 2 holes relative to the neutrality point per Moiré unit cell, this first term is actually annihilated by a ferromagnet. Okay? So why is that? Because, you see, if you place 1 particle per this hexagonal site in the same spin and same valley, then the only thing you pick up is the density term. The hopping is prohibited because it's the same spin and same valley. And so this term is gone when it acts on that state. This just simply counts how many sites are occupied. At n equal to 2, it's 6 of the sites that are occupied, divided by 3 is 2, and that cancels the n equal to 2 here. So that gives you 0. Okay? So a ferromagnet is a ground state of the system. As you see, it's very, very different from the standard superexchange mechanism, which would have given you an antiferromagnet. Now, it turns out that, however, this is not the end of the story, because as I told you, there is an SU4 symmetry that allows us to rotate between the spin and valley freely, which means that we can take this ferromagnetic state, so fully spin and valley polarized state, insulator, and then perform a global SU4 rotation into a state that, in fact, although it is an SU4 ferromagnet, it's actually not a spin ferromagnet. It's a state which you can think of as a valley, intervalley coherent state, where on each site you would make an equal superposition of the electron from one valley and the other, and if you give it an opposite spin, then in fact the total square of the spin will only scale like the particle number, not particle number squared, unlike in a standard ferromagnet. There was a question.
That small n, can I interpret it as kind of like chemical potential?
Yes. Exactly.
What's the question?
If the little n can be interpreted like a chemical potential. All right, so we see that one member of this SU4 manifold, which is the SU4 itself, is still ferromagnetic, so it's still the highest weight. But it's actually not a spin ferromagnet, because the S total, so this is the total spin in the system squared, does not scale like the particle number squared. So if you take a square root of this, this will give you the moment. Divide per site, you divide by n, it goes like 1 over square root n. So in the thermodynamic limit, you actually lose the magnetic moment per particle. Okay? And so the state like this would actually be disfavored by an in-plane magnetic field. It turns out that the kinetic energy would actually favor this sort of an intervalley coherent state because, so I forgot to mention this, because you see there's a 50% chance that if you take an electron with spin up in a particular valley, you can still hop it over here because there's a 50% chance that it's actually in the opposite valley on this side, an opposite spin, and then you can bring it back. So now you can do super exchange within this reduced SU4 manifold. Okay. All right. It turns out that, curiously enough, we can also build some one-particle excited states exactly as well and compute their energies. These are not necessarily the lowest energy excitations, but these will be insulating states because they're basically product states. And so we can then compute what would be the gap, at least a bound on the gap to such a charge excitation. And of course, it would be finite and suppressed by a Zeeman magnetic field.
And these gaps are obtained purely in the absence of kinetic energy.
That's right. And it's also not the smallest gap. It's only for the exact excitations that we can build. We cannot prove that these are the lowest excitations.
So you cannot prove this gap.
It's a product state, so it's going to be gapped. Okay, but it's just an estimate of what you expect for the gap. Okay, now we can't solve the problem exactly for one particle or one hole per unit cell in this Hamiltonian. But we have a candidate if we assume that this coefficient is small. As I said, in the calculation, it comes out to be about 0.7, so it's not small. But if you allow me to treat it as a perturbation, then we're going to first solve the problem with just a cluster Hubbard term. And at one particle, let's say per unit cell, you will want to occupy 3 of the 6 edges of this hexagon. Remember, each one of these contributes a third of a charge in the middle of this hexagon. So this will give us 1 per unit cell. And then, if you then treat alpha 1 as a perturbation, you'll find out that there's a direct exchange term, which is, of course, ferromagnetic. And then, of course, there's a super exchange term, but it turns out the super exchange term cancels. And so you only are left with the direct exchange again. And the best way to then optimize this is to create as many ferromagnetic bonds as possible, subject to the constraint that 3 of the 6 sites are occupied, in order to keep the charge 1 in the center of these plaquettes. And you cannot make all 3 of these bonds ferromagnetic because somewhere you would violate the 1 charge per plaquette constraint, but you can make 2 ferromagnetic. And this will give you a peculiar state in which the translational symmetry is broken. So this looks like a stripe phase. But remember, the charge is not sitting at these centers. the charge is sitting in the center of the hexagons. So if you were only looking in the vicinity of where the density of states is peaked, you would see this as a featureless state, more or less. Okay? Although it actually does break translation symmetry. For those of you who are familiar with the stripe states in the higher Landau levels, it's similar to this. Okay? You gain on the direct exchange, and by clustering the centers together, because they have a large radius, you actually don't lose too much on the charge homogeneity.
But you don't have charge density wave, but also you break timers, so does it mean you can...
No. There is a charge density wave, except for it's not built up where the peaks, where the largest charge density is, because there's still some charge density here. So there's going to be some weak signature. The system still breaks translation symmetry. I'm just saying that the biggest term is not.
But there's charge density and homogeneity, but you're saying it's small.
Correct. Because most of the charge sits in the AA sites. And as you can see, each one of these will donate a third to the center. And so it will look, if you only looked at the centers, it will look essentially homogeneous to you. All right. But this is only true perturbatively in small alpha 1. We don't quite know whether this is correct when alpha 1 is of order 1. Now, we have some unpublished results where we find that the energy of a state like this, so period 2 stripe, using a completely different method, is indeed very energetically competitive. Whether it's actually the ground state or not depends on minute details of the Hamiltonian, which probably are not under experimental control anyway. Okay, and if this is spin polarized, then the Zeeman field would strengthen this sort of an insulator. Okay, so I guess I finished a little early, but it's always good. The summary would then be, I showed you a method for constructing symmetry-adapted, maximally localized Wannier functions and the corresponding low-energy model for the 4 narrow bands in the twisted bilayer graphene near the magic angle. As I showed you, these Wannier states have a peculiar 3-peak structure around the Moiré triangle lattice sites, but they are centered on the dual honeycomb lattice sites. And unlike the usual strong coupling limit of a simple atomic insulator, so Hubbard model, we are finding a peculiar SU4 ferromagnetic insulator in the strong coupling limit at integer commensurate filling. Okay, so thank you.
If you add in inter-valley mixing at some order, what direction is preferred in this?
Yeah, it would help this inter-valley coherent state. Because you now have a process which will take you from one valley to the next, let's say, and back, as long as you can, as long as you can do that process, you're going to lower the energy. Right? So if you valley polarize a state, you will frustrate that sort of a term.
Maybe it can be selfish and insert one of my own questions. So you mentioned if you enforce time C2T symmetry, then it's impossible to only restrict to these.
And a valley you want.
Right. Then if you try to build tie binding model, you need more bands. And my question is, now your one-year state will look completely different. Right? Then to which extent does assisted hopping, this
Right.
ferromagnetism conclusion will still hold?
Right, so that's a fair question. So let's imagine we carry through this program.
Yeah.
What it would mean is that you have to include the remote bands.
Right.
Now, if it is correct that you want to start in the limit where the superlattice band gap is larger than a Coulomb interaction, and the Coulomb interaction is larger than the bandwidth, you will still want to project onto the narrow band. So when you start with a model, let's say 10-band model, or something that now has more Wannier states, which respect the lattice symmetries in a simple way, in this model, you will have a separation of energy scales. You will have the parts of these Wannier orbitals will be living at a high energy, and the other parts at low energy. So if you project back, you go back to something like this.
So I think
so that's point number one.
My understanding this argument is that you're saying energetic arguments dominates over symmetry arguments.
Correct. Right. So that's point number one. Point number two is you could rather easily convince yourself that even in a block basis, which is not obstructed in any sense, a ferromagnet will be annihilated by a density operator projected onto the narrow bands. Okay. So the only other question is, are there other states which are nearby? Okay. And this local approach gives you some sense about why it's ferromagnetic as opposed to antiferromagnetic at low energy.
I have an open-ended question about how sensitive are your results to gauge transformation and Wannier functions?
Okay, right. So, so as I said, we can try to do this calculation without building exponential localized Wannier states. Right? Let's say we do DMRG, which we do in a particular basis. It's not published. What we find, unfortunately, DMRG cannot be done with all the degrees of freedom per unit cell because the Hilbert space is unfortunately too large. But if you, let's say, are in a spinless case and one valley case, okay, then we do find this period 2 stripe at half filling as a very competitive state in a completely different basis. Okay. Now, if you try to understand, and it's not period 3 and it's not period 4, period 2 is among the states which do not break C2T is the best. Okay. So if you try to understand this from a block picture, you'll be hard pressed to see that. If you try to project Coulomb interaction even onto a hybrid Wannier state, so they're partially localized, even then it's too complicated to actually understand why this is happening. But if you choose this basis, where everything is exponentially localized, at the price of C2T not being represented in a simple way, then period 2 stripe will come out rather simply. So I think there are aspects of this which are well, every gauge is created equal, but some are created more equal than others, as you know, right? Because you can see the physics better in them, right? For example, quantum anomalous Hall state, which is also a competing state, can be easier seen in the block basis. Okay, it's not that you cannot see it in this basis either, because the transformations are all unitary, right? So it has to be the same thing. But again, some results are easier seen in a particular gauge than the other.